Yeah, thanks a lot, Vanya, for the very kind introduction, and also for setting the stage, to focus more and more on this circularity thinking, and really how it can bring and offer solutions to the current existing waste problems on global scale. So first, before diving into the story, three things. A shout out to the Ellen MacArthur Foundation, because they published this picture focusing on the energy transition. And they highlight renewable energy is only half of the story. And they highlight that we can only succeed and realize the energy transition if we complete that picture with the circular economy. And so this really tells us if we design windmills, batteries, solar cells, and anything the like, those materials need to be used in closed-loop systems. We cannot continue our linear thinking, and we really have to start designing things circular. So that's the mindset of today that I would like to stress a few times. And of course, this mindset is rather new. Just a few years ago, we coined the concept of circular chemistry, and to highlight that in the broader sense, and also to highlight all the possible solutions that we need. Again, to stress, like Kathleen did before, sustainability and circularity now is truly the platform that will highlight all of these solutions that are now so urgently needed. And if you truly want to become part of the community that focus on developing solutions and sharing them with each other, I really would like to stress the invitation of us to join the Select Route Review Committee community. You can send your CV to the email address indicated here, and also, of course, on the website. And as an example of how that research and this circular thinking can be about, I will share a few thoughts that come from my lab. But not before highlighting the editorial that we published recently, showcasing once more the scope of the journal, and also highlighting once more the importance of circularity. Final shout outs, of course, to my group, because it's truly inspiring to see them working in the lab and thinking about circular solutions that we develop for quite a number of elements at the moment. Not only phosphorus, that will be the key focus of today, but we cover more and more elements of the periodic table. Speaking of which, it was 5 years ago when we celebrated the 150th birthday of the periodic table, and the European Chemical Society launched that celebration with this new version of the periodic table that you may have seen before. And when I first saw it, I thought it was quite shocking, because at the same time, while we were celebrating the periodic table, we highlight possible scarcity that is upcoming. And to me, this truly highlights our current focus and on linear value chains, and our current focus on linear thinking. Because in chemistry, we're used to start with a resource, design a reaction and convert it into product. And then typically we don't bother about how to get the materials back and remake them. This also exemplified in this periodic table. Now, at the other side of things, another concept is the planetary boundaries that really nicely, but also quite scarily, highlights our global waste problems. And so shifting away from a research focus, resource focus, much more to a waste focus at the end of our current linear value chain. And what is interesting is that quite a number of these key global waste problems that we're tackling, climate change, our nutrients that are so important for food production, but are currently also being wasted in the environment, you can connect basically the 6 key biogenic elements to these waste problems. And if we then look back at your periodic table, there is no such thing as a shortage in resources on hydrogen, carbon, nitrogen. But at the same time, these elements cause our major global waste problems. And so my message is basically for every single element in the periodic table, we need to design them much better. We need to make them renewable. so that we shift away from the resource focus and much more to a product focus and the design of those products in a circular system. Let's highlight our current challenge. Again, on phosphorus, this is basically a picture from the Observer that highlights that scientists warn of phosphogeddon as critical fertilizer shortages loom. So we're depending on just a few mines on planet Earth where phosphate rock can be harvested. And at the same time, we waste it on global scale, so that actually we create a major environmental problem where nutrients cause large-scale algae growth, and of course negatively impact the ecosystem over there. So that disturbance of the phosphorus cycle in nature is actually known for quite a number of years. It has been published in Nature in 1944. So basically the problem is clear for a number of decades, but apparently we need to focus much more on the solutions. And this is also basically the message in this paper that we published recently, is that although modern chemistry is pretty much awesome, there are still a few things that we need to change in the way we design chemistry and chemicals and chemical products in general. So not only focusing on resources and convert them into products, but really design closed loop systems. So in short, in order to solve our current problems, the way how we use resources and at the end waste them, we need to truly design a much more different system, and we need to do it quite rapidly. So radical changes is indeed needed. Let's highlight the way forward. Vanya already highlighted the circular economy and the need for circularity, and in this picture, this really becomes apparent. So now we take resources, we make products, we use them, and we lose them. In a recycling economy, we optimize the reuse a bit, but what's lacking is the design of products that can be made efficiently, but also that can be recycled very efficiently in order that ideally there is no waste at all anymore. So in this picture was of course advocated by the Ellen MacArthur Foundation, the concept of the circular economy. And when I was teaching this concept, I thought, well, but what about chemistry? And then actually we need also chemical technologies that can fulfill this ambition and that can actually realize the circular economy, but designing closed loop systems. So in that sense, we focused on chemistry, where a strong focus on design, a strong focus on closing loops, and at the same time, of course, adhering to all the sustainability goals. Now, for today, I would like to focus on the element phosphorus, and the reason is shown here, because phosphorus is life's bottleneck. There is simply no substitutes, no replacement possible. So we need this element. So actually, we should treasure it and use it wisely. So while phosphates are currently popping up in the environment more and more, the way forward is to focus more on the recovery and also, as a second step, more on the recycling. And actually, that reminds me of this gentleman. You may have seen this painting before. It's the 17th century, where an alchemist called Heinrich Brandt, he was really looking for the philosopher's stone, turning lead into gold and really trying to do magic things, which he did, because he created this fire where, he was desperate finding the philosopher's stone. So actually he was condensing hundreds and hundreds of liters of urine, the presence of carbon and some sand. But actually what he did is he chemically reduced phosphates in urine to the element of phosphorus, which does not occur in nature in that form. So this discovery really sparked the interest of phosphorus chemistry and the development of the phosphorus chemical industry. And what he showcased is that we need to do that using renewable resources. But for some reason, our society truly did not want to scale up his procedure. So we went to look at mines, and there are a few. This is a mine in Morocco owned by OCP, and there is still plenty of phosphate in that mine. The problem, though, as indicated before, if we use it in a linear fashion, and most phosphates are converted to phosphate-based fertilizers. I always say once a fertilizer needed to grow crops on arable land, it's always a fertilizer, and if it comes in the waterways, in the lakes, in the oceans, then it remains a fertilizer. In this case, causes a lot of green chemistry, but in this case, what we don't want, because it truly impacts negatively the environment. Solutions to a more resource-efficient phosphorus chemistry are indicated in this review, where we highlight focus on recovery, and ideally the focus on recovery needs to be fully in sync with the subsequent step, which is the recycling, to use the renewable phosphates recovered from the environment and then to design new recycling techniques. So when we were thinking of actually doing that in our laboratories in Amsterdam, we truly were inspired by Hennig Brandt. And how can we actually benefit from this nice mix of nutrients that are water soluble? And would there be a way to actually facilitate the recovery? And actually, struvite can do the trick. And so if you add magnesium in the form of magnesium oxide or magnesium chloride, then ammonia and phosphate are binds with magnesium, forming the insoluble struvite, magnesium ammonium phosphate. And as such, you can actually generate a stream of renewable phosphate that you can harvest. And that phosphate is actually of higher quality than the phosphate that typically comes from the mine that contains cadmium and uranium and other elements. So this phosphate is actually pretty pure. Even if you do that at a music festival that we did a few years ago, where we focused on citizen science and really showcased next to main stage, where we had pretty much the best toilets over there, we highlighted that circular chemistry can be done on large scale, and the quality of that struvite that we produce there is truly indeed sufficient for the next step, and that is recycling. Very interestingly, that recycling wasn't developed at the time, so we focused heavily on it, developed the SysPhos process, and actually also founded the company SysPhos. So the idea is that, for example, struvite can be regenerated at wastewater treatment plants, and then can be used as renewable resource in the synthesis of, for example, ammonium phosphate, where magnesium is needed for the recovery, is not needed in a product, and actually the magnesium can go back to the wastewater treatment plants, where actually the new production of struvite can again continue. So at the moment, SysPhos installed a pilot plant while we were starting with a few milligrams like 5-6 years ago. Now the company SysPhos is truly designing a reactor, designing a factory, and the ambition is truly to make this happen on larger scale. And it's so fascinating to see this adventure that started with a vision. We need to develop circular chemistry and really focused on the chemistry of how to do this. So looking back at this overview of waste problems that we need to tackle, the example I gave you really fits to this design products for recycling and design recovery and recycling schemes. And so for many other large streams, we need to develop in practice this, think of plastics, think of many other elements, and come up with products based on that. It all adheres to the EU Green Deal, but that has an ambition to develop a non-toxic environment. But truly, how to do this, we need much more examples that really showcase this. So as a second example, I would like to focus on novel entities in this scheme, that is basically the man-made chemicals. And in particular, I would like to focus now on organophosphates. And this scheme, how to design molecules for circularity, was published by Klaus Kummerer and James Clark. And for the products that you actually cannot recover and cannot recycle, or maybe do not want to recycle, think of pharmaceuticals ending up in complex waste streams. Those products you actually need to design completely differently so that they still have their function, but actually if they enter the environment for one reason or the other, that they actually mineralize and that the elements are taken up by the biogeochemical cycles. So if we think of organophosphates, there is a huge challenge that we took up in the lab, because currently the synthesis of organophosphate also starts from phosphate rock. Now phosphate rock is not converted into fertilizer. Phosphate rock, just like the production of steel, where iron oxides are reduced to iron, phosphorus oxides are fully reduced to the element of phosphorus, just like Hennig Brandt showed us to do that. Industrially, this takes place at rather high temperatures, using carbon and silica, as I mentioned before. And then, while phosphate in the oxidation state 5 first goes to phosphorus in oxidation state 0, subsequently, it is again oxidized with chlorine gas, and it's further oxidized to POCl3, and then subsequently the organophosphates are actually prepared. So you can imagine that we're currently developing a much more sustainable synthesis that ideally connects directly inorganic phosphate to organic phosphate. And at the same time, we're also focusing on redesigning the organophosphates, because which ones do we actually need and which ones fits perfectly in the circular economy. And to highlight the need for the design of new products, some organophosphates that are actually used as flame retardants are detected in the environment, so that's not good. And secondly, some of them actually show toxic effects. So it's truly, if we redesign organophosphates for large-scale applications, we also truly have to avoid any of the toxic side effects in the environment. So we started a framework that basically focuses on how to do this better. And we selected an organophosphate that currently is produced in industry and also currently is detected in small amounts in the environment. Second, we generated alternative structures, really almost millions of it, as a random ID generator, because how can we design a better alternative? Next, we predicted of all of them the properties in terms of biodegradability, toxicity, environmental fate, and also we looked at the ease of synthesis. And then we ranked the properties, and actually the top 10 structures really were interesting, because what we found out is that branch chains are now suddenly linear. And this is actually known from literature, that the linear alkyl chains are easier to degrade in the environment. So that we confirmed. And second, we found this ethylene glycol substituent that we thought that's also rather interesting. And so now the target structure had been selected, then we went to the lab to actually make it and actually experimentally determine the properties. And actually, that's currently ongoing work, and I just can highlight a few results. And what we found is that the standard alkyl organophosphates, they behave as a flame retardant, but actually the designed ones, the redesign, behaves better. And so this is in collaboration with Sabir Gan from EMPA and his team, where it really shows that it passes the vertical burning test. So that's promising. And that's why we heavily continue this way of thinking of redesign of current chemicals that are needed, but redesign them such that they actually can behave much better in terms of their properties in case they enter the environment. So you can imagine that this organophosphate, we identified the chlorine atom as a hazardous structural fragment, and then we came up with a redesign, a known molecule, but currently not used on large scale. And that's something that we're actually interested in to explore further, because the phosphate core, we can produce that from wastewater treatment, renewable phosphates. The ethylene glycol is always an interesting molecule because it can directly be produced from the biorefinery. Avantium here in the Netherlands has a process to convert glucose with hydrogen to ethylene glycol. So that can be done efficiently. And at the same time, that hydroxy group facilitates the biodegradability of the organophosphate. And so all in all, the organophosphate is needed for its flame retardant properties, and actually designing the molecule as such would also facilitate its role in the circular economy. So with that, I really would like to showcase the way chemistry needs to move forward, where obviously we need to focus on converting resources into products, ideally renewable resources that we convert into renewable products. Second, there is an essential focus needed on circularity, but we need to focus obviously on realizing resource efficiency by making product more durable or more reusable or more recyclable, where in the end we also develop large-scale recovery schemes that will allow the recycling of those materials. And all in all, this comes together with a key focus on safety and safety of the environment and human health in particular. So with that triple focus of chemistry, there are a lot of challenges, but also lovely adventures that we need to take up in order to use chemistry for a much more better world. So with that, I would like to end once more highlighting the journal, Sustainability and Circularity Now. It's apparent why we need circularity, but it's also clear that we need to develop much more solutions, new chemistry that actually adheres to this principle. So with that, I would like to thank you for your attention and look forward to the discussions.